Hey, what's up guys? Here we are, back again for some more tutorials. Um, so we're still up to Model 2. We're here. Looking at the PNNL paper. The last video we looked at the paper a little bit. Look at the paper by PNNL. It's really good. We're using AI to help us understand it, and then how to create some code in Python to make sense of it and kind of make some pseudo code format. So yeah, and we've been kind of looking at Model 2, and then it's so similar to our Model 0, which was just the constant degree per minute, but it actually takes in like a ratio based on weather. So I've been actually glad that we are going through this in more details, because I went through the Vibe Coder repo and actually made some significant updates to it, including this one too. So hope you guys are getting something out of this. I definitely am. Made some significant updates to the Java code, and I have it set up at a large VRF building. So yeah, so like in the Java code format, which we're not getting into very much. So we studied how we're computing minutes. That's based off of this alpha parameter and the delta temperature squared plus a b alpha parameter. So this is delta temperature. If you remember, it was the zone temperature before the building starts, where it would be cold or warmer than the occupied zone set points. So that's how we're calculating delta temperature. It's that zone temp that needs to be conditioned before the building starts. And this model is a quadratic representation of that. Then we tune these alpha parameters, and the units on this was minutes per degrees cubed plus another additional minutes adder. So yeah, that's I have this running in a full-blown Java format in the Niagara framework. A little bit of computer science magic that calculates some of these error parameters. And also the computer science algorithm captures the elapsed time it takes to recover the zone, which is like pretty critical for any of these models. So Model 2, which we're at, linear degree per minute, and then PNNL. Yeah, so that's just this, the linear degree per minute, and then PNNL. We've been talking about Model 2 is taking in this ratio of these temperature reference, and also the what the outside air temperature was yesterday, comparing it to today, and ultimately this little block computes a little bit of a minute calculation, total minutes. And then we just add that to our degree per minute total minutes. So that's I'm also testing this out in the field. So made some pretty significant updates to my Vibe Coder repo in the Java versions, which I'm testing this out. So maybe in the future we can actually look at that a little bit. So where were we? So we were at in the lessons, and got a long ways to go here. So out of 50 days, yikes, we're at day 17, looking at the ratio for Model 2. So let's just go over model day 17 real quick. Looking at the ratio, Model 2 multiplies the base warm-up time by a ratio derived by outside air temperatures. The formula is Tref, outside air temperature, and outside air temperature today. So here is our mini example. So Tref, I think that was just the was T-ref again? So many of these. Okay, so yeah. So for heating mode, T reference is 32 degrees, and for cooling mode in degrees Fahrenheit, it's 100 degrees Fahrenheit. So like the white paper describes these as a reference point that basically the HVAC system could run continuously. So they're saying at 32 degrees outside Fahrenheit in Wisconsin, that's not that cold. I would put this down to like minus 10 Fahrenheit. And maybe in Wisconsin, we could run HVAC systems continuously because it's so cold outside. And then the T-ref for cooling mode is 100 degrees. So perhaps that's the outside air temperature that we would run HVAC continuously because it's really hot outside. And there's also metric conversion for that too. In the vibe coder repo, there's actually an input where you can use imperial equals true, and you'll use the imperial units, or if use imperial slot as false, it defaults to the metric. So here we go. So we talked about, we did this earlier, calculating the ratios, and then why does the ratio blow up as the current outside air temperature approaches these T reference. So this basically blows up, explodes that extra minute calculation because it's, there's math behind that. But it's the idea is to run the HVAC system continuously. Okay, so let's just jump right into day 18. Go back to day 17 if you want a little more detail on that. So here, let's go with day 18 out of the way, and maybe we can go a little bit further, depending on time. So goal, derive indoor rate before applying the weather adjustment. Model 2 first computes large base alpha 2 parameter from yesterday's warm-up data. The PNNL paper defines alpha 2 as this temperature set point minus I think that's zone temperature minus the delta temperature minus 1. It's essentially the inverse of the degree per minute. So the inverse of what we did for model 0. This value captures quickly the zone warm. This value captures how quickly the zone warmed yesterday before any weather adjustment. Then you can use the alpha 2 parameter to predict today's base time and multiply it by the ratio from day 17. Okay, so getting more into the weeds of this, so let's make our little handy dandy Python snippets here. We can kind of look at this in more detail. So we can just do Python math lesson script. Shoot, this is not correct. I'm gonna go back to, so we were just kind of looking at these math. I'm just gonna do it in this script. Doesn't really matter where you put the code in, it's just for learning purposes. Okay, so what do we got here? So compute the alpha 2 parameters from yesterday's data. This is just pretend data, and predict today's base time. So delta T yesterday is 8 degrees. This is degrees. I'm in Fahrenheit where I'm at. Increase from yesterday. So this is just yesterday's performance, basically. So we just kind of pretend that um, maybe perhaps 2 hours before the building started up, that our zone temperature got, because the HVAC is off, it got colder. So we're cold building, we're 8 degrees below our occupied heating set point. So that's what that is. And then this would be yesterday's actual warm-up time performance. So that would be where our computer science algorithm captured 40 minutes. So basically we captured for 8 degrees to condition our zone. The HVAC system took 40 minutes on that particular time. So that is our alpha 2 parameter. Degrees per minute. So baseline time for today is, so let's say our delta T today is 6 degrees. So not as bad as yesterday. All right, what are they doing here? I have to look at this to see how different this is from our model 0. Predict the base time for today. So this is just calculating minutes. Same exact thing we did on these earlier lessons, where it's just we're still calculating degrees per minute, and then we're just solving for minutes by dividing. So that's how we get 30 minutes out of a degree per minute calculation. Yeah, so alpha 2 is just our linear degree per minute. Pretty easy. Okay, if yesterday's was 10 degrees in time, compute alpha A. What is it? 10 and 45. So this is the same thing we did in the Model 0 tutorials. If you want to reference that, that's pretty similar topic. So pretty basic stuff. So this is where we're at. 0.222 degrees Fahrenheit per minute. Base time today is 27 minutes. And then this called 5 degrees. So 5. Here we're at 22.5 minutes. Nothing too crazy. So why is alpha A an essentially the same as the linear? Yeah, so it is essentially the same. We just talked about that. Okay, so maybe we can just jump right into doing another lesson if we got enough time, which I think we do. Okay, so let's try and pump out 2 days. Sometimes these lessons get a little monotonous, that I can just, if I have the time to maybe try and keep the videos for sure under a half an hour, 20 minutes is the ideal. We can do 2 days in a lesson. Okay, so combine base time and weather ratio to compute the final runtime. Model 2 performs 2 steps. Predict the base time using yesterday's indoor rate and multiply the weather ratio to account for the outdoor differences. The final optimized start is T opt T base times the ratio. Seems kind of straightforward, I guess. Okay, so what do we got here? We got quite a few lines of code. So sometimes I just have to separate this out so it makes a little bit more sense. So this is our alpha A. This was just our ordinary degrees per minute, which we did the last time. Then this is the same thing we did with the last lesson. Our delta T today is 6 degrees. So now we have this this is our base time. And I'll just put a print statement in here. Print base time minutes t base. Okay, so our base minutes for our model is 30 minutes based on this data. So t ref. Okay, so this was our, if you remember, t ref, this was our extremes. Doesn't really say it here, but we're in like a heating mode. 32 degrees Fahrenheit was our extreme, just our initial like parameter to just say the HVAC system runs continuously. If it was metric, we would put that to 0 degrees Celsius. Just what PNNL defined as almost like think of it as a design day parameter, I think, where in HVAC, the HVAC design, the mechanical engineers, they have design day references where basically they size the HVAC systems to meet some kind of extreme weather conditions, wherever that zone is in the world. And so I'm kind of thinking it kind of like that. So that's what tref is. In the Java code base, I have a tref heat and cooling, imperial and metric. So we're in heating, 32 degrees, outside air previous, outside air current. So this was yesterday's. I almost wish they would put this up here, because this is kind of like yesterday's data, and we should put almost, for me, a teacher to understand it, that yesterday's outside air temperature is kind of grouped with yesterday's data, but oh well. So maybe we could just do a print ratio colon over there and just say ratio Alright, so here we are. So it is the it's basically the T base times the ratio, which is correcting for weather. Cool. I just realized that I've had on the vibe coder repo in the math formula, I just realized I have something wrong. In it, I was actually had a plus symbol right here, but it's where we need to multiply because it's a ratio, so we'll have to fix that. But yeah, so that's kind of neat. So it actually, factoring in the outside air temperature, we correct it. And I think that we'll get into that these numbers, like we'll be tuning these numbers and this ratio, we'll constantly be predicting a little bit different numbers. So this degree per minute will always get tuned, and it seems like this should get tuned as well, but maybe it doesn't. So that's a big deal. At least like I said before, if this was Wisconsin, like I would say minus 10 degrees Fahrenheit, or perhaps even minus 15, that I would consider, maybe 0, I guess. So yeah, that plays a big impact. I'll have to think about that a little bit, but it's not, at least it's making sense to me, so hopefully it's making sense to you guys too. I'm kind of curious just to glance at So we only have um, 2 more days left before we get day 22. I think would be Model 3. So it's kind of curious, like maybe maybe we should just answer the questions first. Okay, so without jumping into too many days in the future, which I tend to do, maybe I'll just save these for tomorrow. Okay, use your own outside air temperature, your own delta temp and outside air temperature to compute Model T. Okay, so let's see. I think So explain why these two-step calculation is easier to tune than a single. Explain why the two-step calculation is easier to tune than a single combined formula. Also think about that. At least the way that I'm looking at it is like this is one step and this is two steps, so it's just easier to understand, I guess. So on that question, so under what conditions does Model 2 reduce to Model 0, which is just an ordinary degree per minute model? Model 2 has that outside air temperature correction. So under what conditions would the ratio turn out to be 1, basically, because we multiply it. So if we multiply by 1, it would be the same as t base. That's all I have to think about. So there's something here, like it basically, if it would be like, I'm just gonna make up some numbers here. So if I would just say 31.1, let's say we can just say 32.2. So if all of these numbers were very similar to our t base, that actually blows up the ratio. So that blows up the ratio, which makes sense, because as if our outside air temperature was at this kind of this critical design parameter. So let's say if we were 60 degrees Fahrenheit, it would be very mild, nice spring conditions, maybe getting some shorts and t-shirts out. Yeah, so look, our ratio turns to almost 1 because we're really warm outside. So yeah, that's really interesting. I just makes sense. I feel like people should be like if you're installing this in the field, like you would almost want to reference like what ASHRAE zone you're in, because this will be completely different depending on where you're at in the world. So here I'm almost kind of curious just to like ASHRAE zone map. Oh, come on. Cloudflare. Let's see if we can look at this image and this looks like a nice image. Yeah, this is great. Okay, so like I'm up here in this blue area that's pretty cold. It's pretty much like Canada. And if you get really cold, like here you are in Canada, Alaska, Siberia, and these, Antarctica. Then if you get way down into like the red, very hot and humid, you're like full-blown like Cuba, Florida, Papua New Guinea, parts of China, Australia have this very very hot climate. So Brazil. So these are going to be way different. Like if you would put, my point is, like if you would put a T reference for here, yeah, 32 would be appropriate. But up here, 32 degrees Fahrenheit, people are going to be not quite shorts and t-shirts, but they're going to be, this is a nice hot day. So that's going to really kind of affect their model potentially. I'll have to think about that, but it is almost like a nice reference starting point, I guess. So I have it running in the field, so maybe we'll just find out and see how it operates. So that is all for this video. So stay tuned for tomorrow. I think would be days 20 and 21. Enjoy your weekend.